Okay, part number 2. How do the assumptions and sort of parametric assumptions in particular interact with the correction for multiple comparison approach that you choose in your study? Let me start with a very brief recap of what we discussed last time, plus I want to bring in one additional method, which is the method of permutation. So you'll remember there are two main families of corrections: family-wise error that control for the probability of any false positive across all the tests we're doing. We saw Bonferroni, we saw random field theory, and as I said, I will add permutation to it today. And then the second family is false discovery rate, where instead of controlling the probability of getting any false positive, what you're controlling is of the claims that you make, in other words, of the voxels that you report as being active, what proportion of those are false discoveries. So Bonferroni, you'll remember, fairly intuitive. The idea is that if you want your family-wise test to be corrected at 0.05, you simply divide that by the number of tests, parallel tests that you're making, and that number is the number you want to use for each individual test. Now, the good sides of this is that it adapts to the search volume. So the greater the search volume, the greater the correction; the smaller the search volume, the smaller the correction. It also has a very strong control of type 1 errors. In other words, you're very unlikely to make any false positive claims. It controls that very well, or rather, it prevents you from having inflated alpha errors. However, it does come at the cost of a lot of type 2 errors, a lot of false negatives. On top of it, because it's so stringent, on top of it, MRI data violate one of the basic assumptions of Bonferroni, which is that the parallel tests that you're making are independent of each other. And as we discussed last time, this is not the case because over space, the signal is dependent in fMRI, is autocorrelated over space. And this, of course, leads to even further type 2 errors. So yes, we do control very well type 1 errors, but this comes at a great cost of a lot of false negatives, which is why very few people today do a Bonferroni correction. Now, the approach number 2, random field theory, probably one of the most frequently used approaches today. And as I said, this is just a way of finding a threshold in data sets such as fMRI, where you can't really say, well, here's how many independent variables I have, like voxels or something like that. You remember, it's a 3-step approach. You first estimate how smooth your data are, and you do this based on the residuals. Then you compute the Euler characteristic, which means if you set the threshold, if you think of this particular graph down here, how high a threshold do you need here so that you get at most the desired number of false positives, 0.05, and then you take that threshold and you apply it to your data. The beauty of this is that you can do it either voxel-wise or cluster-wise. We typically discuss it at the cluster-wise level, which is the way I've presented it, just because very few people ever do this at the voxel level, also because it is overly stringent. It's already fairly stringent, I have to say, under the right conditions. At the cluster level, it's even more stringent at the voxel level. And you'll remember that in plain English, what this means is given how smooth my data are, which is the number of results, how high up a threshold, in other words, how high up does the z need to be, so z being the vertical component on this graph, how far up does the threshold need to be so that I get at most 0.05 chance of getting a significant blob in null data. And the good parts of this is that it's just like Bonferroni, it adapts to how many results you have. It also adapts to how smooth your data are. So it follows the characteristics of your data and it adapts to them. However, it does come at the cost of a large number of assumptions, and that's why I'm doing this little recap. First, we're assuming that the distribution of data is fairly Gaussian. In part, this is also why we smooth our data in preprocessing. Then the statistic has to be sufficiently smooth. Typically, fMRI data turn out to be smooth enough at current resolution, but this is something that needs to be empirically looked at. The spatial autocorrelation function has to be twice differentiable at the origin. And then if you want to do this on, so this is for, and these first few assumptions are for any type of correction. If you want to do cluster correction, you also need to have the data must be spatially stationary. And I'll get into this. And the smoothness of the data has to be well estimated from the residuals. Now we're going to take another participant, and again we're going to flip. We're going to flip the labels. We're going to take another participant who did have the intervention, and we'll pretend they did not. And then we'll take another of our participants who did not have the intervention, and we'll pretend they did. And we'll again take the subtraction of the average score across the two groups, across the red versus the blue. Again, under H0, is there no effect? It shouldn't matter, right? There should still be no difference. And when we take the difference between the reds and the blues, turns out the number, the average distance is this. And then, and sort of we keep going, right? Then we, now we have these three, now we take, these three, and we say, no, we pretend they didn't have the intervention. We take these three, we pretend they did have the intervention. And now we do reds minus blues, and we get this number right here. And we keep going. We do all possible permutations. So what happens is that we will get a distribution of statistics, or of the difference between the reds and blues across all these possible permutations. Then what we do is we take the original difference, the original value of the statistic, the original difference between reds and blue, and say, what are the chances, how unlikely, or how extreme rather, is the statistic I get, is the difference between reds and blue I get under the original labeling scheme, compared to if I shuffle them. And if our number is extreme enough, then it's very unlikely that it comes from the same distribution, which means we should reject H0. It's not the case that, which means that labeling actually does matter, right? So there is an effect of my intervention. So this is how you would do a permutation testing. Now, this too can be used at a voxel-wise or cluster-wise level. The beauty of it, the whole motivation for it, is that it's non-parametric. So you can entirely do away with all of the usual parametric assumptions and not bother with all the problems that we discussed so far. At least theoretically, these type of analysis only require what is known as exchangeability. The only assumption is exchangeability. Now, subjects are exchangeable, meaning under H0, whether you're in group A or group B, since there's no difference, doesn't matter. If I switch, you out of one group and put you in the other, it doesn't affect the other participants, right? There's no correlation between you and the other participants. So this works very well at the subject level when you're doing group analysis, because at the group level, we can exchange subjects. And so this works well. It does not work well at the first level analysis because fMRI volumes are not exchangeable. And this might also help you understand what exchangeability means. If you think of it, imagine under H0, we just have an fMRI time series. And as you know, the fMRI time series is autocorrelated, which means each time point is a function of the time point before, plus or minus some new error. So it's a positive autocorrelation. Now, this means that if I take one volume from here and I put it somewhere else, it's not independent of the volumes around it. So in this sense, I cannot take two volumes and randomly change them, because each volume is inside a certain autocorrelation structure. So for this reason, I can't simply take a volume from here and a volume from here and switch them around because they're autocorrelated. So for this reason, you cannot use a permutation approach on a first level fMRI analysis. You probably could use it if you first pre-whitened the data, but typically we don't care as much about our first level analysis. The place where we really do our inferences is at the group level. So people typically do not do this. I should say, and we're going to discuss this a little later, turns out there are circumstances where your subjects are not exchangeable. What if you're doing a repeated measure studies? Obviously, the observation at time point 1 for a certain participant will be correlated to the observation at time point 2. So if you're doing a before-after. What if you're doing an analysis on families or twins, right? The twins are probably more correlated than any other two random participants. So if that is your circumstance, you need to use what are known as exchangeability blocks, but I will cover that a little later. So finally, if the data are normal, then the analysis overall is less powerful than if you're doing a parametric approach. However, if the data are not normal, then your permutation analysis at least is valid. And as I said earlier, there are a number of different approaches that will, a number of different tools, I'm sorry, that will allow you to do this exact analysis. And finally, the last type of correction that we have seen is known as FDR, or false discovery rate. And the idea, as we said earlier, is to control of the positive claims you make, what proportion of those are false positives. And the idea in terms of finding out how to do that is that if you order from the smallest to the largest all the p-values of all of the voxels in the brain, you're going to declare you're going to declare a certain number of them to be active, such that the last one that you declare active, the p-value of that one is smaller or equal to the number of voxels that you're declaring active, so all the green ones, divided by the total number of voxels time alpha. Okay, so you have to order them, and you consider active all the voxels up to and including the one for which it is true that its p-value is smaller or equal to the number of voxels we're going to consider active, so all the green ones, divided by the total number of voxels time alpha. This gives you usually greater sensitivity, and we've seen that in some of the simulations that I presented when we discussed this originally, but it does come at the price of increased type 1 errors. In fact, you're guaranteed, you know that 5% of what you're observing is false positives. 5% of the claims you're making are false positives. And so in this sense, this also leads to a certain lack of spatial precision, because you look at an FDR corrected map and you don't really know, you cannot point at any single one of those active voxels and say, that one is active, because you don't know, that could be the 5%. And it's tough to know which of the active voxels is the false discovery, or is the 5% of false discovery.